The characteristic function of a random variable x is a tool as a transform method that transform the PDF of x into another domain. The definition of CF or characteristic function is very similar to moment generating function. It's expectation of e to the I omega x, where I is the square root of minus one, the imaginary number. Uh, and as you can see, that for the moment generating function that we happen to use the same phi, the same notation. MGF is e to the tx. So for the definition of characteristic function, it look as if we replace t as I omega. But the concept is different because for CF, because you're taking the expectation of a complex number, what you interpret here is actually a complex integral. And for this is the continuous random variable case, so that's why you take the integral of PDF probability density function with e to the I omega x. When the random variable x is discrete, you interpret that expectation as a sum, and this sum take over the range of k or xk, whatever the range space of that discrete random variable is. By taking a look at this form, you see that the definition of characteristic function, one thing is that, oh, very, very closely related to MGF, just it looks like it will replace T by I omega. But I'm gonna explain shortly after this that there's gonna be some differences in the properties between CF and MGF. And one thing I would like you to take a note is that this looks like a Fourier transform. So recall the Fourier transform of a signal in time domain. That is that is e to the minus omega I t e and f t dt, right? So we always have these square root to, oh, sorry, it's I have to move. Okay. So the Fourier transform by the definition is this, right? And remember that the factor of 2 pi thing is just a normalized factor that it can either be on the Fourier transform side or it could be on the inverse Fourier transform side. Or these normalized fraction can be taken in a symmetry, right? So for CF is actually, it looks like the inverse Fourier transform, all right, of a signal, where the signal in this case is fx. But people say in a loose term, in a loosely speaking, that oh, CF is simply the definition of the CF is simply a Fourier transform of PDF, or probability density function. Okay. We have this concept that every pos every probability density function and its characteristic function form a unique Fourier pair, which means whenever you take a look at this at a particular random variable with its own unique PDF, that's going to correspond uniquely to a certain characteristic function. Okay. Um, So, and this is what I said earlier. What I said in previous video that MGF form a unique pair with the PDF is actually, I talked about that in a loose sense. What I actually meant is that CF, because CF is very related to MGF in this way. Okay. So the benefit of having CF is, of course, as I mentioned before, whenever we don't know about the distribution of a certain random variable, we can derive the the CF characteristic function first, and then try to see if that characteristic function is something that you already known, or does it match with some distribution that you know. So in that way, you can conclude about the distribution. The reason why it's called characteristic function is because that expression itself, phi of omega, it's uniquely characterized that random variable. Okay, because of the reason that PDF, and characteristic function and a certain distribution, these are, unique tuple. Now let's talk about the characteristic function, the property, and I'm gonna note the things that that is different from the MGF. First of all, the characteristic function always exists no matter what values of omega. Okay, CF, right, is expectation of e to the I omega x, but MGF is expectation of e to the tx. Okay, let me go back to the MGT a little, because what I explained earlier about the MGF is that um, this value doesn't have to be valid for some t, and you have to be able to derive the range of t, the set of t for which the integral is finite, is valid, and that's going to be the domain of phi t. That means for MGF, or for some value of t, makes this integral invalid or diverge. On the other hand, the characteristic function has a nice property that this integral always exists. This integral, or this the summation, always exists because we have this result in complex integral. If you try to find the complex integral, okay, suppose wt is let me just use, I don't know, let me use another term. Ah, maybe just use, if I have some complex integral, all right, my x and y are real part and imaginary part, all right, of some real value dummy variable t, that complex integral is always bounded by the integral of the modulus. This is a result from complex analysis. Okay. Therefore, the modulus, the modulus of the CF is always bounded by the integral of the modulus. Okay. This is a modulus in terms of the complex number. But because the modulus of e to the I omega x is always 1, omega and x are supposed to be real number. All right. So, and then that ends up with integral of the density function, which is 1. Okay. That means your CF is always bounded by 1. It never go diverge. So this is a first property that CF that is different from, this is not true for MGF. How can we achieve that upper bound that is less than 1? If you evaluate at phi 0, that is the that is the e to the I 0 times x fx dx, right? And that is 1. Actually, that upper bound 1 is achieved when omega is 0. The third property, the characteristic function is always self-adjoint. Self-adjoint mean in this context is similar to an even function definition. Phi at minus omega is the complex conjugate of phi. Okay, the star notation is simply taking the complex conjugate of that value. This is very simple. Phi of minus omega is e to the e minus omega x, and by the definition is e to the minus omega x fx dx. Okay, and because e to the minus omega x is simply its own complex conjugate, right? So that's why it's equal to phi w, phi omega, and then take the complex conjugate. Last one, this is a nice property about uh, characteristic function. If you have the double sum, this term, this looks like you're taking the characteristic function, evaluate at some difference between omega, some w, sorry, not omega. Sometimes I use w, sometimes I use w, sometimes I use omega, sorry. And you can take a look at this as a function of z, where phi is a coefficient. And because you have double sum, it looks as if this is a function of quadratic function of zj. It turns out that this quantity always non-negative. Okay. Why is this double sum property very useful? It has some connection with a lot of things. Uh, you're going to see similar results with autocovariance function when you learn about random process. So let's prove this property. Okay, I have the double sum of jk, phi of omega j minus omega k, zj zk star. All right, I'm going to derive that it is non-negative. First of all, I apply the definition. So phi is going to be integral of ei omega j minus omega k fx dx, and then multiply with ci zk. Okay, and that is equal to, and because I know that and now what I'm going to do is that inside this integral is the integral of x, but my z are supposed to be just some complex number, all right? This complex number doesn't involve in x, so I can also put it inside the sum. Sorry, inside, I mean, I'm not sure if you, okay. This is a double sum, or this is a double sum of the term in the red bracket, all right? But under the red bracket, it involves the integral that are indexed by j and k. And after you're done with the integral, you run the index with j and k, all right? So what I mean is that this doesn't involve in x, so it can be either inside, either be inside or, sorry, it can be either inside integral or outside. So now I'm just going to move it inside to form the term. So I'm going to have e to the I j cj, right? And I'm going to have another term, e to the I minus ik ck star, and now dx. But because I can also write it as cj here, because e to the I omega k zk star, I can write that is a whole thing, star, right? This term, this minus term, is just the complex conjugate of this term, and the complex conjugate of the product is the product of the complex conjugate. Okay. So now what you can see is that you have the double sum of the integral, right? It's going to be the same as I take the sum first. I mean, the double sum is linear, right? I can either uh, put the integral outside, right? And dx. Mm-hmm. Okay, next I would like you to take a look at this double sum. It seems like you have double sum of this guy, and this guy is very similar to this, except that it has complex conjugate. So think about this as some aj, and then you have bk, right? So AK star. So when you have the double sum, when J and K are equals, you're gonna have AJ star, right? And then when j and k are not equal, you're going to have like all the possible cross term between aj and ak star. For example, this double sum goes like this. This double sum goes like the modulus of a1 square, modulus of a2 square, the dot goes all the way, dot, 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 right? And then you're going to have the cross term a1, a2 star plus a1, a3 star, dot, 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 right? And then you're going to have again a2, a1 star, a2, a3 star, dot, 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 until all the all the remaining terms. So these double sum are actually, I mean, can be written as a1 plus a2 dot dot dot, right? a1 plus a2 dot dot dot, and complex conjugate, right? So this one turn out to be a1 plus a2 dot 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 dot. This is sum up to n, right? Modulus square. So this term double sum, I can write this double sum as the a1 plus, sorry, now I'm going to replace a with e to the I omega 1 z1 plus e to the I omega 2 z2 dot 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 e to the I omega n zn. Modulus square. I think I miss fx. I miss fx dx, fx dx. Okay, until this term I have fx dx. So we arrive at this integral that you have j equal to 0, j equal from 1 to n e to the I omega j cj modulus square fx dx. So you're going to have an integral of non-negative number with fx, which is always non-negative. So this integral must be always non-negative. Okay. So this is a property, the last property of characteristic function. Now I'm going to show that from the result that we derived from the lecture video of MGF. In that video, I have derived that MGF of Gaussian with mean mu and various sigma square. These can be written as e to the mu t times e to the t square sigma square by half. All right. So from the definition of the CF, right? That is e to the I omega x. Now we can just take a look at this. It looks like you can replace t equals I omega into the expression. So that's why the CF characteristic function of normal is going to be e to the I mu omega times e to the minus sigma square omega square half. You get the minus because when t equals I omega t square, you get the minus, right? Because I square equal to minus 1. Okay, and this is what we got here. We have derived that MGF of binomial is p plus, sorry. From the previous video, we have derived that e to the t plus q to the power of n, everything. Again, that's why for the MGF of binomial, you can simply replace t with I omega. And for the Poisson phi, which is MGF, is e to the lambda e to the t minus 1. This is from the previous video. That's why for characteristic function, you replace t with I omega. Okay. Um, and also we have similar results that when you have a transform variable y equal ax plus b, you can prove the same way. Um, CF of y at omega is going to be expectation of e to the I omega x, sorry, I omega y, right? And because y is an F transformation in x, and that gives you e to the I a omega x times e to the I b omega. Sorry, I think in the previous, okay. Mhm. So it looks like, so this term e to the I b omega can be taken outside the expectation because that term is deterministic. And now we have e to the I b omega. And this term, this is expectation with respect to x. And it's actually the what? The CF function of x evaluate at a omega. Okay, so this is how we derive the first result, how the CF function is changed under the F transformation. Okay, now what else? What am I supposed to say? Uh, There's one, so I'm going to explain how to apply the concept of characteristic function. As I said earlier, characteristic function form a unique pair with the PDF, right? And that gives you a unique pair of the distribution function of x. Okay. We can extend the concept of characteristic function of two variables as well as a function of several variables as well. In this scenario, and when we have x, right? When we have x that has CF as phi x, and suppose we have y as and with the corresponding characteristic function as phi y, right? The concept of characters of the new function random variable x equal z equal x plus zy. The question is this. Suppose we know the distribution of x and y. What about the distribution of the sum? That's a simple question. We can apply the same concept of CF, but now we can derive the CF of z. Because we're going to use the fact that once we get the CF of z, because CF form a unique pair with the density, form a unique pair with the, distribution function or whatever that variable is. So why don't we, if we want to know about the distribution of the sum, why don't we derive CF first and see how it turns out? Okay. In this example, I will derive a general result first. So by the definition, it's going to be expectation of e to the I omega z. And because now I'm going to take the expectation thing in detail. All right. So I plug in z as a function, as a sum of x and y. And because you can split, right? You can split into the product of exponential. Now, I would like to take a moment here to make a note that this expectation is with respect to joint distribution of x and y, right? Typically, it's supposed to be the double integral of e omega x, e omega y, joint distribution of x, f x y, dx, dy. But I'm going to assume something that simplify this derivation. I'm going to make another example that x and y are independent, all right? They are independent. If they are independent, what turns out to be is nice because you can I mean, the expectation of function x and function y can be written as the product, right? For example, if x and y are independent, whatever you have here can be split into ex and ey square if they are independent. So I use one more assumption. Okay. Now, with this expectation, we recognize that whatever inside the expectation involves the variable x only and involve variable y only here. So that turns out to be cf of x, right, times cf of y. And that gives you a nice result that it just simply say cf of independent CF of the sum of independent RV is the product, all right, is the product of the CF. This is the general result in the yellow box. Now, how about we apply to some of the examples here? Suppose I have two independent binary random variables. Suppose I have x, that binomial, with n1 with probability of success as p, and I have y as independent, another independent binomial random variable with the same probability of success, but the number of trial experiments are different, n1 and n2. The question is, and also x is independent of y. Uh, my question is, what is the what is the distribution of x and y? I'm going to use a technique from the CF transform. So I'm going to derive the MGF, the CF of z of the sum. And I use the previous result that it turns out to be the product, okay? And because we can make use the results here, phi x is going to be t e to the I omega plus q n1 times p I omega plus q n2. This is for y. But because you know that they have the same base, so you can just sum the exponent. Okay. At this step of derivation, the question is, you know the distribution of x and y, but you don't know yet the distribution of the sum. But after you have applied the property of the CF of the independent sum, it turns out that the CF, has this expression in the green color. From here, you use the fact that a CF must be uniquely corresponding to a certain distribution. But what you can see is that it takes a form of another binomial random variable. It's just another binomial with um with this parameter. So we can conclude that x plus y is another binomial random variable with with n plus n1 plus n2 and the same probability of success p. Okay? Does it make sense? Next. How about I'm just gonna remove to this line. What about if you have the sum of Poisson? Suppose my x is Poisson with rate lambda 1. My y is the rate of lambda 2. Like maybe you can think of, sorry. You can think of these x and y as the number of car accidents. For x is the number of accidents in junction x, and y is the number of car accidents in junction y. And these two junctions, they have different rates. They have different rates of events. Maybe at junction x is more often, that the car have accidents. And these two junctions are independent. The question is, if I make the sum of these two variables, what kind of variable does it turn out to be? Okay, we derive the same thing. We use the same fact that if x and y are independent, the CF of z of the sum is going to be the product. And we take the form that we obtained earlier. So that is e to the, for x now, you're going to apply with lambda 1, right? E to the I omega log minus 1. And for y, for CF of y, you're going to apply lambda 2. Mm-hmm. And again, because, I mean, what is this? This is just the product of two exponentials. You know, you can make the sum of, you can make the sum of the exponent at this stage. This is what you got. You got the CF characteristic function of z. And because CF function form a unique pair to the to the distribution, to the corresponding distribution, now you recognize that this is just another Poisson CF, because it looks as if this is the Poisson expression, but the rate turns out to be lambda 1 plus lambda 2. So you say, in this case, um, my Poisson, the sum of two independent Poisson is going to be another Poisson with the new rate, and the rate is going to be the sum of the two rates. Okay, so this is an example of how you can make use of the transform method in 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 recognizing distribution function of random variable. Okay, so I hope that you do the exercise. The thing is, for given distribution, can you derive the CF? And under F5 transformation, can you apply the property of F5 transformation and derive the new CF, and and make use of the result that we explained here? What about the new distribution of the sum of two independent random variables?